do some of those other examples that are shiggly, I decided to use a problem that I used a couple years ago. So this is 2 years ago, I think. This is the homework problem I used. So I have 10 samples of axial force, and I have 10 samples of yield strength. They're down below here. And they have nothing to do with each other. They don't correlate with each other. There's just here's 10 numbers we got from the force applied to the thing, and 10 numbers we got from the strength. And we know that both of them follow a normal distribution, right? So we want to find the probability that a strength is less than 35 KSI. And this is A36 steel, by the way, so it's already, hopefully the average is near 36 KSI for the yield strength. We want to find the design factor for a reliability of the rod for 80% reliability. We want to find a design factor required for the rod for 99% reliability. And we want a safety factor that's associated, the safety factor and associated reliability if the preferred size is specified for this one right here, right? So we're gonna use this design factor with the 80% reliability. We're gonna pick out a preferred size, a diameter, and then we're gonna go back and we're gonna say, what is the reliability now that we've used this? And there might have been something wrong with this problem when, so there might be a reason why I didn't use it here. But when I'm going to start here, let me start with an Excel spreadsheet. And what I need to do is I need to get the standard deviation. I need to get the average and standard deviation. I can easily do this by hand with I could easily do this by hand if I had just the average, but here I also want to get the strength. I want to get the standard deviation. All right, so 42,424. I used a random number generator for this, by the way. 753, 47244, 41645, 40. This is exciting, right? 836, 43, 532. I'm probably going to make a mistake somewhere. 40783. He said it probably as he was making a mistake. 44321 and 45473 and 47738. Boom. And up here, 37251, 37104, 33 847, 36972, 33690, 3545, 234 913, 37214, 37135. Oh, I missed one. Oh, I missed the last one. 36959. All right. So that was a tremendous waste of your time. But here, what we want to do is hit average. So we take the average of this, right? That's fine. And maybe do this, and then maybe I'll put in a column right here and say average. There you go. And then go stat dev. All right, so it should be a little hot. There you go, boom, right there. All right, here we there's two different types, right? We can have standard deviation, P, or standard deviation. So if you start to type it STDEV, you'll see with the dot P, and that's based on the entire population given as arguments. But you could also have S, which is standard based on a sample, ignores, okay? So S is actually technically the correct one, dot S, right? I don't think I need it. I think I just need to go parentheses now, right? And so just come down here, boom. So you can kind of see what these values are, 44, and let me make it bigger. All right, 44,000 is the force, right? And the standard deviation right there. So you could see here's the average 36, like it should be 36 KSI, right? So that's good. So let me see. I'll write that down. I'll write these values down on here, right? So I have my mu F is going to be 44,075 pounds, and my standard deviation of F is 2,644. Let's call it. Let's see what I had in the previous one right here. Woo, boy. Yeah. Okay. So actually, this is interesting. Let me see if I got. Let me see the thing wrong. Let's see. I tell you I see my values in mine. Let me try and see what happens with the P instead. Right. Let's go P in there. Yep. Okay. So I printed them out right. You can see the differences between here. S is the correct one to use, but in my old notes here, I have used the P when I should have used the S, because it's a sampling, right? And we want to have this, so it's the this is in the population of thing. All right, and so anyway, let me go through this. I'll just proceed as with the correct thing. So the strength right there is 36,054 psi, and the standard deviation of the strength is 1,447 psi. So what I want to do is I want to get my okay, so the first question that I got asked was, what is the probability that it's less than 35? So what I need to do is get for using the strength right here, I want to have my x minus mu divided by sigma hat. So I'll say 35,000 minus 36,054 and divided by my 1,447, and I'm going to get 35,000. 36,054 subtracted out. Of course, it's negative. 1,447 divide, and I get a negative 7284, right? And if I'm going to do this by hand, which there's no reason that you have to. I'm not sure more learning takes place, but desert island kind of stuff here. Let's go 0.72 or 0.7, and here's 0.72, and here's 0.73. So it's between these two right there. So you want to interpolate, and so you make an interpolation table. So we have 0.72 and we have 0.73. Ours is 0.7284. If you've never interpolated before this way, it'll be new to you. Yay. So the answer in the book here is, and this is something you would need to know if we were to do this on an exam, and I don't know if I would do it on an exam, but maybe I would. 0.2327, and I always call that x. And here is the scheme to find x. We want to do the same thing on the left side as the right side, so we take, and I like to go 0.73, subtract this from that, divide, subtracting this from that, right? So we're using the bottom one as the means of comparison, and I didn't leave myself enough room. I'm going to take that and subtract it from there, right? You see we subtracted this from that, so we have to subtract that from this. So 0.2327 minus x divided that minus that, right? So as long as we are being consistent right here, we'll be fine. So I can pretty much easily do this. Take 0.73 minus 0.7284 divided by 0.73.72 minus, obviously, duh. So I get like, this is going to be 0.16, right? So that's like sort of like the percentage of that gap right there. We'll multiply it by this, 0.2327, 0.2358 minus, and then we're just going to multiply that. It ends up being a negative number. That's okay. I want to make sure we keep that negative correctly right here. And now we're going to take that and subtract that, right? So we're going to 0.2327 minus, right? But then it's going to be a minus number. So I find that I get 0.2332, right? 196. And okay, so that what that says to me is that there's a 23.32% chance that it's going to be less than 35 KSI. Is that what it said? The probability. Yep. So that is the probability. Oh, I have a phone call from unavailable. How much you want to bet this is going to be about my car insurance? Hello? Hello? What is this regarding? Association. Okay, so all right, so let's see how we would do this in Excel, by the way. Let's say, so first off, we would take my Z, right, for this one, and maybe I'm going to say, let's put the 35,000 right here. 35,000, so here's going to be equals, parentheses, 35,000 minus my mean, right up here, that guy, divided by my standard deviation, and I want to use the correct one right there. And yes, I get the same thing that I had, duh. But then I can get, now I want to say, I called it R, but maybe I can I'll go R. We'll call it R. Right, so the command that we want to use to get R is going to be equal to norm.s.inv. Right, and put that guy in there. Whoop, and I said S, X instead of S. Nope, it doesn't like it. No. Let's see. Should we make it negative? Nope. All right, pause. Pause, you stupid son of a... All right, made a mistake. You want to take... I think it's the DIST. DIST. I went the wrong direction. I confused myself. You want to wear true, right? And I think, boom, there you go. 0.23319. Hey, look, my interpolation was pretty good though, right? Wasn't too bad. 0.2332, right? So those right there, that's actually the percent chance, right? 23.32% chance. Wee! All right, so let's go to the next part of this thing, and that was okay, so that's the first one. The design factor and required diameter of the rod to achieve 80% reliability. Okay, so what we want to do First, we have these parameters. Let me see. First, I have these parameters. The equation. Okay, so the thing I need to know is I need to know the stress coefficient of variance. So the stress coefficient of variance is going to be C sigma. That's the same thing as the coefficient of variance of the force. So we're going to use that. It's the standard deviation over the mean. I keep getting that confused. So it's the standard deviation of force over the average force, or 2644 divided by 44075. 2644 and 44075. We get very small number, 0.05. Ooh, very, very, okay. 0.05999. Woo. And then we're going to go strength coefficient of variance. And so that's going to be this guy, and he's going to be, I keep doing the wrong one. About to say a bad word. I'm not going to know. Mu s, and so that ends up being 1,447 divided by 36054, and so 1447, 36054, divide it, and 0.04013. All right, so our design factor, I'm not going to rewrite this equation all the way out, but we could maybe come back into here and see him. Where'd he go? This guy. This is the equation that we want right there, right? So 1 plus or minus and all of this stuff. We need the z. All right, so that's one thing that we need. So let's look that up for 80%. Are they going to give us? Are they going to give it to us for 80%? No. We'd actually have to go hunting for that. All right. So for 80%, they're not going to show it. We need 20% instead. All right. So we would be hunting for. There you go. Very close to 20. So we can expect this to be 0.84, right? Or 0.84, between 0.84 and 0.85, but very close to 0.84. So this video is already too long, so I'm not going to do the interpolation, to go backwards interpolation, to be able to figure out what where it is between 0.84 and 0.85. What I'll do instead, I'll do an Excel. So I don't know where to put it. I'm just going to put it over here. Here's 0.8. We would have equals to, and I think that we're going to get the norm.s.inv of this 0.8416, right? So we got it in between there. So let's just write that down. That the z for 80% is going to be equal to 0.8416, right? And then we plug that back into this equation right here, this very long equation that was 1 plus or minus the square root and all kinds of stuff in there. 1 minus z, and then the first it's going to be which one is it? I guess it goes CS first. It doesn't matter, does it? 0.04013 squared, and that's going to be times 1 minus 0.8416 squared. Now we're going to use this one, 0.05999 squared, right there, and divide. And now we're on the denominator, we got 1 minus 0.8416 squared, and it's CS. So it's this one, 0.04013 squared, close, right there. All right, so pause while I hit my calculator. All right, so what I end up getting is 1 plus or minus this right here, and that turns out to be, I think 1 plus it, and I think at 1.062. Not a very large design factor, but we're going to go run with it anyway, right? And so the allowable stress is going to be the yield strength over the design factor, and the yield strength, or the average yield strength, was 36,054 divided by 1.062. So we have the allowable stress 36,054. We get 33,951. These are PSI. I haven't changed to KSI yet. And if we wanted to find the diameter from this, we already kind of did a problem where we had that, right? Where I said stress was equal to F over A equals F over pi over 4D squared. So we would say that the diameter is going to be the square root of 4F. And if we set this one to allowable, I'll go allow. It doesn't save that many letters. Get rid of it. Pi allow right here. Put that into there. We're using the average force 4 times, so that's the 44,075. And this is the 33,951. What we're left with here, according to this, is we need 1.354 inches, right? And right, so now go to the preferred sizes. 1.5. But you notice actually, if you notice your fractions, that's pretty close to 1 3/8, and that doesn't seem too bad to me. I kind of like the 1 3/8 better than 1 1/2. But let's. I also have the choice of maybe going up to a preferred size, right? So I might go 1.4, right? So I mean, I go going up to a preferred size in decimals. So we could go to 1.4. That would save a little bit, maybe. I don't know. Try it out. So we could either say D was equal to 1 1/2, or let's say 1.4 inches. Right there. That's the one I decided to choose. And then I decided. See, I'm not going to do part C where it asks up for 99% reliability, but we got a similar thing is going to take place, right? No. I just made a mistake here. I'm sorry. This was not the correct number. I apologize here. That was not the correct number. If I do this, I was cheating and looking at my Excel spreadsheet I had just made. That was for the 99% reliability. This is 80% reliability. That's why I have such a small value right here. If we stick this value in there, I think I get 1.286. And in that case, I'm going to go with 1.3 inches right there for 80% reliability. No, this is 80% reliability. This one right here, this is rounding up to the preferred size, right? So now what I'm going to do is I'm going to design for this. So I'll figure out the stress, and I'll use my 44,075 and divide by pi over 4 and 1.30 squared, right? And if I do that, I'm saying that my stress is going to be 30,615. So my safety factor actually for this is going to be, so I'm going to take 36,054, the strength, divided by the stress, and I say that's going to have a safety factor of 1.26. All right, so do not use more than 2 decimal places when reporting a safety factor. But now let's say for my preferred size, right? So now I need to do one last thing. I haven't demonstrated one more step. So one step that I could do is I could find out what my reliability is going to be if I have that design factor. Let me double check that I'm doing this correctly. Okay, so I'm going to have this, this is my safety factor. I want to plug that back into this equation right there. See this equation? I can get a Z if I put that design factor or this factor of safety back into this. So let me get that equation down. I'll write that Z is equal to negative n minus 1 divided by the square root of nd squared cs squared plus c sigma squared right there. So we already have those coefficient of variances. So the only thing we really have to do is take this and put in my 1.26. So that 1.26 is actually, so I don't want to drop any sig figs here. Just so you know. Okay, so this is what I'm reporting, but here's what I actually got. 1.2, I just lost it, 1.2592 right there. So when I plug it back into here, I don't want to lose any, get any error because of this. So let's see, 1.259 is good enough, minus 1, divided by the square root of 1.259 squared times CS, which we go all the way back up to here, was 0.04013 squared plus, and we'll go with this guy, 0.05999 squared. And what do we end up with? 1.259, subtract out 1 from it, 1.259 squared, and then 0.04013 squared times, and then 0.05999 squared added, square root it, divide it, and I get 3 point, and by the way, it's supposed to be negative, 3.302. Okay, and so we could look that up in our table A10, but chances are we're going to have to interpolate. It's always on this last line, basically. This last line right in there. We'd have to find in between here, right? So we have 3.3, so somewhere in between these to find our reliability. So let's instead use Excel and in the command here. So we want reliability from Z, right? So I just calculated the Z. I'll plug them in here. I'll try to get it a little bit more. Sig figs 0.30226 is what my calculator actually said. So the reliability that I will get is going to be, where'd you go, man? How come? Get probability from Z. That's what I want. I want norm.s.dist, and from here, comma, true, boom. Now I want 1 minus that. There you go. Boom. 99.95% reliability is what I get if I use that. And let's see, yeah, 99.95% reliability is what I end up getting from that. So there you go. There's a problem worked out long ways, all the way through. Very similar to your homework problem. The only thing I didn't do is I didn't do part C, and that's really just a variation of part B, just so that we can have some kind of means of comparison. What I would have done then instead is I would have now replaced this Z right here with the 99% one, which I could find from here, right? So there's 99% right here is going to be 2.326. Did I get that right? Let me see. 99, Z for 99. Where'd you go, Z for 99? Z for 99% chance. I don't see you. How come I don't see that calculated anywhere? Let me check this thing out. Z for 99. Why don't I see you? Seems like that's something I would have calculated in the middle. So let me see the here's what I get with the Z for 99, right? So if I go, there you go. Here's the 99.99. There's my 2326, right? And that was the one that I said that, right? 2326. Yeah, that's what's out of the book right there. 2326. So I would use that one instead of this, right? Is that true? Yeah, I think so. Yeah. I'd use that instead. Let me see this is an old one. 2326. Yep, 2326, sure. And then what I end up getting for my safety factor instead of when I plug that into here, I get my design factor, 1.18. That's what I need. I need a 1.18, and the 1.18. Oh, there you are. There's the Z for that. Okay, 1.18, 1.178, and then I end up getting a diameter, required diameter of 1.354. And then I get, so then I pick out 1.4, which is much higher, right? So much higher. Yeah. And I'm trying to think about that. It's just a good thing to compare, right? Based on reliability. So, done.